So what this slide shows you is the following. So I was trying to look for this equation, which we sort of had, looks like we had skipped. Somehow the slide got skipped. But anyway, here's the equation. The net torque is equal to rate of change of angular momentum. And I had already mentioned this net torque is equal to internal torque due to internal forces plus torque due to external forces. By the way, this symbol is tau. Tau. Oops. TAU, tau. Okay. So net force torque is due to internal forces and external forces, and that's equal to dl by dt. And this is always 0. So what we have is external torques. So on a system, only external torques can change the angular momentum of a system. Okay. And if this is 0, then this will be 0. And L will be constant. Okay. So we'll see some spectacular applications of this fact. We'll look at systems where the external torque is 0, and we'll see the systems evolve. And as they change, what will remain constant is throughout the change in the system, the angular momentum will be constant. Okay. And so that's what we'll see. All right. So here's an example of this. Okay. And in this example, so apparently it's you can do this from as low as 3 feet. Okay, so what this shows you is you can, if you have a cat, you can grab hold of the cat with its legs and drop it. And what you'll find is, as long as the cat has a tail, what you'll find is the cat will always land on its feet. Okay, and I guess you can actually YouTube videos and stuff like that. So here's one YouTube video. Okay. And this is an application of that equation. So the external torque on this system, the only force of so this equation is valid for this system. The only force acting on this is the force of gravity. And when you calculate the torque about the center of mass and the angular momentum over the center of mass, the external torque is 0. And so the angular momentum of the cat should remain constant. So what this is saying is the angular momentum of the cat at every point in its fall is the same. Okay. And so if you grab the cat with its leg, when you dropped it, its angular momentum was 0. And so its angular momentum should be 0 through the entire motion. Now you can see from these things that the cat's body is spinning in this direction. So it obviously has an angular momentum in this direction, which is a vector pointing in that direction. So what is really happening is the cat makes its tail spin the other way, and so its body can spin this way. And the angular momentum of the tail and that of the body add up to 0 at all times. And that's how the cat lands on its feet every time. Okay. And apparently, I guess as long as you drop the cat from about 3 feet, this is good enough for it to land on its feet. And also, of course, it needs to have a tail. Even if it doesn't have a tail, it probably can turn its hindquarters in one direction and the front in another direction. Okay, so an application of this fact: external torque is 0 and angular momentum remains constant. Okay, so here's another application of it. So this is with regards to the solar system formation. So our solar system, formed from a cloud that was about 5,000 angstrom. And 1 angstrom unit is the Earth-Sun distance. Okay, so it formed from a cloud that big, and the cloud was slowly spinning. And the current size of the solar system is, so the outermost planet is about 50 angstrom units. Okay, so the furthest planet is about 50 times as far as the Earth is from the sun. Okay, so this cloud collapsed into that object, into an object that, okay, so it collapsed into 1/100th its original size. Okay, so and this started about 5 billion years ago. So the initial cloud had an angular momentum. It was spinning, and the angular momentum was in that direction. Okay, so the final product, which is the solar system, has the same angular momentum because there's no external torque acting on this. And so as the cloud collapsed, it was spinning faster and faster, just like when a skater, as she folds her arms and legs in, she spins faster and faster. So the entire solar system now, which is made of objects like this. The sun is spinning and the planets are going around in that direction. The total angular momentum through the entire process for 5 billion years has remained constant. Okay, so here's a spectacular example of conservation of angular momentum when there's no external and there's no external torque acting on the system. Okay. So here are a couple of other applications. This is the reason why we throw a football with a spin. If you throw a football on a windy day, if you didn't have a spin, the force of the wind would make the football wobble. And when it wobbles, the friction force increases, is variable. And so it's very hard to predict where the ball would go. And so it's hard for the catcher. Now, if you give it a spin, the orientation of the football remains constant because the angular momentum will remain constant. And now the friction force, since the orientation is constant, the friction force is predictable. And so your supercomputer, which is the head, your head attached to your shoulder, can calculate where the ball will end up. And so it's easier to catch. So that's why we give the ball a spin. Same reason we give satellites a spin. If you give the satellite a spin, any debris hitting the satellite won't make the satellite wobble because and if there's an antenna, if those satellites start pointing in another direction, you won't be able to reflect your signal off the antenna. Okay, so that's why we give the satellite a spin, so it'll always maintain its the direction in which it points. All right, and so here's another example of conservation of angular momentum. So here's the system, and again, there's no external torque acting on the system, and so whatever changes, so if this guy is spinning, this guy is spinning, since there's no external torque on the system, no matter what changes happen internally within the system, the angular momentum of the system will remain constant. L will remain constant, and L is I times omega. So as the guy brings the dumbbells in, the moment of inertia goes down, and so angular velocity increases. So when he brings the dumbbells in, he'll spin faster, and he can, as long as there's no friction in this stool, he can keep doing this for 1 billion years, and his spin rate can, and he pushes his arms back out, and he'll slow down, and he can, but his angular momentum will remain constant as long as there's no friction. And here's the classic example of the skater. Again, here's the angular momentum is moment of inertia times angular velocity. And when she brings her arms in, moment of inertia is decreased. Moment of inertia is decreased, and so angular velocity increases. And again, assuming minimal frictions, if she extends her arms back out, her velocity will decrease. Okay. Okay, so here's another example. So you can get this merry-go-round spinning, and if this guy walks towards the center, the moment of inertia of the system will decrease, and this will spin faster. Okay. Now here's a example you might not have seen, and I urge you guys to go find a YouTube video of this. I do this in class, and everybody who sees this the first time really can't believe this. Okay. Anyway, so here's the demonstration. So you sit in a chair that can turn, and you take a bicycle wheel and give it a spin like this. And well, so let's say somebody has got to spin the bicycle wheel and hand it to this person. Now, the total angular momentum of this system is just the angular momentum of this bicycle wheel, which is, it's spinning in this direction, and there's the angular momentum. And now what this person will do is flip the bicycle wheel. So now I'll draw here. So now when you flip the bicycle wheel, it's spinning in this direction. So the angular momentum of the bicycle wheel has gone there. So we'll just give numbers. Let's say it's 20 units. So now this is minus 20 units. But remember, there's no external force acting on this system. Whatever she did was, those were as a result of internal forces. So the angular momentum of this guy, this system, should be constant. So L should be constant. Okay. So since the angular momentum of the wheel now is minus 20 units, how can you make the angular momentum of the entire system constant? So what ends up happening is, to make sure that L is constant, she starts spinning in that direction. And what is her angular momentum? It has to be, for the lady, it is 40 units. 40 minus 20 is 20 units. Okay, so this is really a very spectacular demonstration, and I urge you guys to go see it on YouTube. Okay. All right. Here's another demonstration of conservation of angular momentum. So you've seen these these dives in the Olympics, where a diver will jump off, and in some competition, in some events, you got to spin twice before you hit water, or 3 times before you hit water. And the way they do that is, when they jump off, they lean forwards and then they jump off. So in the process of jumping off, they've applied a torque on themselves, given themselves a little angular momentum. And then if you scrunch your body, you spin faster, and you hold the scrunch. And if you want to do 2 spins, you scrunch it appropriately long, and then uncoil yourself and dive down. Okay, so the more spins you want to do, the longer you are scrunched up, and that's how they control how many spins they do. Okay, so again, all these are spectacular examples of external torque being equal to 0, and so angular momentum is conserved. Okay, L is constant. Okay. And so one of the things you do is, in all these applications, in some of these applications, you play with this. If you increase this, this decreases. And if you decrease this, angular momentum increases. So in this case, you decrease moment of inertia in flight, and angular momentum increased, and angular velocity increased. And so you were able to adjust how many times you spun, and so on. But again, all these are an application of angular momentum being constant. Okay. Now, here's a very spectacular example of precession. Okay, so before we talk about this, let me go back to one of the previous slides of the top. Okay, so let's see, where's the top? There's the top. Okay, so so you saw that if a top is spinning and if there's a force of gravity that's trying to topple this top, what the top does is instead it precesses. Okay, so it'll precess like that. Yeah, so remember that. So if you have a torque acting on it, on this top, a spinning top, the top will precess. Okay, so that's the net result. All right, so let's go back to Earth. Okay. Now, so Earth is out in space. So here's the sun, here's the Earth going around, okay, and there's the moon going around the Earth. Okay, so here's the Earth, and it's spinning on its axis. Earth is spinning on its axis, and now it turns out that if the Earth was a perfect sphere, this would not be possible. But the Earth is not a perfect sphere, and it turns out that the gravity of the sun and the moon. So the sun and the moon exert a torque on Earth, tending to twist it upright. So the forces of the sun and the moon, what they want to try and do is to try and, if the Earth was not spinning, they would make the axis point in this direction. Okay, so they would straighten out the axis. The axis is tilted by 23.5, and so, but since it's spinning, the Earth precesses. Okay, well, how do we know the precession? Okay, so imagine, so here's the Earth. Imagine everything else is, imagine a huge beach ball surrounding the Earth, with the Earth at the center, and that would be the sky. And so every object would be appear on the beach ball. That would be the sky. And so if the Earth's axis is spinning, this point on the beach ball will not move. Everything else on the beach ball would move as the Earth spins. And that point is the North Star. So if the Earth's axis is spinning, precessing, then the North Star will change. Okay. And that's what we have observed. So that's how we learned about the precession of the Earth's axis. So let's see. Okay, so we have historical records. The Iraqi people were spectacular, very good astronomers, and they kept very good astronomical records. Okay, in 3000 BC, that was the North Star. Today, this is the North Star. So you can see that in 5,000 years, the Earth's axis has okay, so in 26,000 years, the Earth's axis will precess once. Okay, so what does this mean? So for instance, here's a simple thing that means, so here the Earth going around the sun, and because of the tilt of the axis, we have the seasons. Okay, so the northern hemisphere is tilted towards the sun, it's getting more sunlight, and it's summer for the northern hemisphere. The southern hemisphere has winter right now in June. Okay, so, and in December, the axis, the northern hemisphere is tilted away, and it doesn't get as much sunlight, so it's winter for the northern hemisphere, and it's summer for the southern hemisphere. So since the Earth's axis precesses, if you come back to Earth 13,000 years from now the axis will be pointing in that direction in June. Okay, so it'll be winter for us in June for the northern hemisphere people in 13,000 years. Okay, so that's one of the effects of this thing. Okay, all right. Okay, so we use this constant, this angular momentum constant fact, if no torque act on it, to turn satellites up in orbit. So what you can do is, here's a satellite, and if let's say you want to turn it, what you can do is you can put a gyroscope, an electrically operated gyroscope in the satellite. And let's say you want to turn the satellite in this direction. What you can do is you can send an electrical signal, spin the gyro in that direction, and the satellite will turn in this direction. Okay. And when you want to stop the turn, you just stop the gyro, and the satellite will stop. And so if you have three gyros that can rotate in three independent directions, you can turn the satellite any way you like. Okay. So that's the idea. All right, I guess I will pause now and let you guys ask questions if you have any.